presentation. First, I want to thanks to the committee organizer for inviting me to this event, and I want to thanks to Marek firstly. And I'm Claudia Moreno from the Physics Department in the University of Guadalajara in Mexico. And this work is about parameter estimation, mainly for the beta parameter in core collapse supernova. My collaborators was Laura Villegas, Miquel Sanolin, and Javier Antelis and Michael Paquias. Okay. The motivation for this work was to take a research catalog in order to simulate a phenomenological and analytical model to analyze the beta parameter, that is the rotational, the relation between rotational energy and potential energy, and to try to estimate the parameter immersed in noise data. This work was published by Classical Quantum Gravity, and this you can see this in the base data. Okay, then I will start to speaking about the rotational parameter. And as you know, the waveforms are emitted by the proton neutron star if it has some rotation. So the rotation in this work that we took was in these two limits, but some of them depends of the physics that you are looking for. Sorry. Sorry. Sorry, it's in the other side. Oh, I finish. Now questions. I can back. Button, please. Oh, yes. Sorry. Okay. Then these three, we have mainly these two parameters that for the beta value, and our target was to look especially in these three models because they have a better shape of the waveform, and that is the main reason. And the parameter beta that we choose are in this value. The beta parameter, as I mentioned before, is the ratio between potential energy and kinetic energy, and this value depends on the rotational profile. And this rotational profile is defined by the maximal initial rotation, the distance from the exit rotation, and the measurement of the degree differential rotation. Okay, so the catalog that we take, as I mentioned before, is the research catalog, which has about 2,000 simulations. They are into these dimensions, about those 12 solar mass, 100 different profiles of rotation, and 18 equation state models, different models. In this, particularly this waveform has the shape like you can see here and you saw in another talks. And one characteristic that they have 3 peaks that we can model in an analytical way. After the 3 peaks, the signal is not so good like the first part, and it's beginning to be stochastic, and we cannot do an analytical model. Okay. So for our first analysis, we took particularly 100 waveforms with these profiles and equation of state. As you can see here, the equation of state that we choose are in this in different colors. At the beginning, we take the signals from the catalog, and we see that they have very, very noisy here in these waveforms. And for this, we use a low pass filter in order to get less the noise in the waveforms. So as Milan showed in this this is the waveform that Milan showed, and we can see that we reduce the noise. Now we will consider only these characteristics for the parameter A and the initial rotations in this range, because we choose these parameters because we saw that they analytically are better, are the best to do the analysis. Okay, so with this signal, then we characterize the peaks with the parameter beta, and in the third peak, because this has, as you see here in the peak, in H1 and H2 is closer, and H3 is not so closer because they start to be more stochastic. Here, H1 and H3 is in the positive range, and H2 is in the negative range. So we now get closer to each peak, and each of these peaks you can see here, but all of these points are the waveform that we use to plot the peaks of the waveform. And in order to find an approximation, we took the second order linear approximation to try to see what of them fit more closer to the beta parameter. As we can see here, in the beta parameter, we have 0.08 in this range, and this is less than this value and plus than this value. So the range that we are analyzing, I said before, is from 0.02 to 0.14. So if we plot every peak, we see here, for example, the H2 peaks is in this way, and the other one that depend of two parameters. The first two depend on the beta parameters. And if we go far from 0.08, this is spread out more the waveforms. So this is very interesting to see this peak, and we can see here the colors that I mentioned before in order to get one approximation and see the continuous line and show what is the behavior of each model. We took here in the GX the maximum, the difference between the positive peaks less the negative peaks. Okay, once that we have the best model that we find to make the phenomenological model, we try to find with exponential terms the waveform that we obtain with in the black. We've showed the numerical signal, and blue is the signal with simulate parameters, the blue, and the orange is the signal with the best fit parameter that we find. So almost all the three has the same shape, but one has more amplitude than the others. So if you see here, then the amplitude is in H1, H2, and 3, and the shape of the form of the waveform is through the potentials. The time is the arrival time for each peak is in the name TA and TB, and the eta is the width of each waveform in this part. The parameters that we choose are here, and with this data we can now obtain we can obtain and do the comparison between the analytical model and the simulate model, and when we compare them, one of them we can obtain the fitting factor, and this fitting factor here in the first histogram is the comparison between one numerical and one analytical waveform. So we find that the best fit in this distribution is around 94 point in this morality in this line. And this other histogram show where we can compare where one numerical simulate waveform and the other 100 simulation dot weight with the numerical signal. It was the second analysis, and this now is the third analysis to try to find estimation parameters of the to find the estimation parameter of the numerical signal. And here we have first the numerical signal immersed in noise, and colored simulate Gaussian noise and in real noise. Here we try to estimate the beta parameter that is that we choose this value, and we can see that the estimate parameter is the same that we choose in the simulation, and the variance of our data is very small because this is 10 plus less 3, and this means that is very, very, very small. And in this, with real noise, this is also very close to 0, and this means that we are doing a very good work with this. So finally, I will speak about the error of the estimation of the parameter beta. I mean, is how true is your beta in the simulation. And with this, we use a statistical method that depends on the variance. The variance the variance here is obtained through the method called Crowd-Lower bound, where I is the Fisher matrix, and this Fisher matrix is the expected value of the waveform, and this here depends of the noise of the signal. So in order to be more precise, we choose a second approximation, and then we have to obtain first the first approximation with the variance, and after the second term with covariance, because this is a matrix and this is a vector, and then together both of them is the sum of them, and then with this value we can estimate the covariance of the parameter beta, and then the error of the beta value is the ratio between these two terms. Okay, then after do this, the sum of these two terms, we can see here the error that we obtain about the parameter beta. And remember, our main point is about 0.08. And we can see here that if the error is in this red line, is 100%. And if we make the comparison, okay, in the matching filter, we did an analysis with real noise and Gaussian noise that are these two dots. And then also we do the estimation of this error with the Einstein telescope, Cosmic Explorer, and LIGO 03. And you see the estimated parameter with Cosmic Explorer and Einstein telescope are very low, or lower, lower than the matching filter, and the LIGO is bigger than the Cosmic and Einstein telescope. And our analysis with real noise and Gaussian noise is around 10%. It's not so bad. It's very good result. And as you can see, the red point is Gaussian noise, and real noise is closer. Is better this value with Gaussian noise than the real noise, because the real noise is more aleatory. Okay, then thank you. My conclusion, sorry. My conclusion are that we can feed a very good phenomenological model for the first part of the core bounce phase. We use mass shell filter, and we are able to obtain the error of the parameter beta and also the variance and the beta parameter. And as I invite to you to see the Manuel talk. I don't have the red color, but it's because he is going to speak about optical analog signal, which are very less noises than the research catalog. Thank you.
Thank you, Claudia, for being in perfect on time. Time for questions.
Thank you for the nice talk. So I have one question about the error estimation. So it's not clear to me. So this is the error estimation associated to the mismatch between the templates and or is the one related to the noise in the detector?
The first one.
The first one.
Yeah.
And the second one, do you have estimations of how it depends on distance or on the different parameters? Or maybe I missed the slide, sorry.
This is slide, no?
So it's the 2 points, no?
Yeah, point with the real noise. It's because this is the beta parameter, but this is the variance.
Yep.
We estimate the error with the variance first.
And this is for a particular distance, I guess.
Yeah, the 10 kiloparsecs.
This is a 10 kiloparsecs. Okay,
yes,
okay.
10 kiloparsecs.
Okay, now. And a particular model with a particular... okay, the beta is there. Yeah, sorry. Yeah.
Thank you.
Now everything's clear. Thank you.
More questions? No. I have a question myself too. If I remember well, in the research paper, they said that the waveforms scale with different parameters, which is the difference between the amplitude between the two peaks and the main frequency. Have you compared the estimation when they use these parameters with other works that use this?
No, not already, but if you have any model, if I need any model, we can do this
Okay.
work for this analysis.
Okay. If there is no more questions, we can thank Claudia again.